Hello. Okay. Yeah, welcome to data structures today. Today was a crazy day. So basically, let's see here. Do I still have it up? So I spent the day moving one of these things, and so that's why I'm basically, I will admit, I am pretty dead. It took 3 of us, and it was hard. So let's try to make this a good lecture on heaps, okay? So we have 1 week. So I moved IDX cabinet, not mine. My apologies. It was supposed to be last Friday when I didn't have class, but nope. Of course, it was today. What else do we need to talk about? So we'll talk about heaps today and leftist heaps. And then we might talk about, well, that's it. Like, if we talk about heaps and leftist heaps, that should be good for today. The project, right, is due in 7 days, 1 week. So at this point, I'm going to be diverting most of my attention. I want anyone who needs any help to contact me, and I will find a slot of time for you. Okay, and I know that right now we only have 12 people watching the stream, but whoever's watching the stream later, basically anyone who is my student, you know, ask for help. Get it. Don't wait. Now is better than never, but also better than late, but also better than 1 day away from due date. So some people have asked me about the exam. I know, so homework 2 has been released. It's like 4 plus, maybe 4 to 5 questions. Hopefully not too bad, is my hope. And then the last thing to talk about, I guess, is that I think what we're going to do is that the exam is I'll release the exam, maybe 10/20 on the due date, and then I'll give you plus 1 week, okay? And so technically I think the exam might have been supposed to be blah, blah, blah this week. I really didn't want to put the exam this week. 10 questions exam? Yeah, maybe around 10 questions. I mean, you know, I know that I'm moving stuff around, but I really just didn't want to do that because, like, if you have a spare second and you're not doing the project or this homework, then you ain't doing the right thing. Does that make sense? So I'm not releasing anything new. We're not doing anything new. It's all the material that we're going to talk about is, you know, all that. So I think that's basically everything. I've almost got the coding part of homework 1 graded. Project 0 should be out this week at some point. So keep in mind that I don't grade the projects. The TAs do, but even they are on the course chair's schedule. So, yeah. Okay. All right. So, when's homework 2 due? Let's make homework 2 due 10/21. Okay. So technically, you'll have 8 days to do it. It's not. And normally with exams, my goal with exams is to get them back in 1 week. So that'll be probably the fastest grading for the class. All right. when I used to grade calc exams, I used to grade them in 1 day, and I usually do grade exams in 1 day, but I'm going to promise 1 week just because I don't want to. Let's try not to overpromise and under-deliver, which is the moral of the story. Hey, dog. Come here. Huh? All right. Want to come here? Yeah? All right, come on up here. Nope. You just want to sniff around? Yeah. Project 1, you're going to have to wait. I feel like maybe... I don't know. Anyway, okay, so if I had any time, right, I would help with the generating test cases and stuff for Project 1, but I don't really have much free time to promise people. Okay, so let's get started with heaps. Today's announcements, I would say, today's announcements, not too bad. Finish Project 4 for 202. Can I still submit? Thank God I don't have to deal with that. Okay. So let's look at heaps. And so I want to talk about heaps as arrays. So let me see. Is this... Let me close the IIDX thing. And pull out my pen. And so... Yeah, I mean... Okay. Yeah, stupid dog. She gets lonely. If only she wasn't so badly behaved, it'd be nice to be able to take her into UMBC's campus. But dog is very bad. Is bad. She's a bad dog. So, okay, so let's talk about heaps as arrays. So really there's 2 operations on a heap. Well, technically there's 3. There's like create. And for the heap here, there's not going to be much. And then there's insert. And then there is delete max. Or I guess really you could... There's the 2 max operations, right? So you have the max. And so you can either find max or you can delete max. And that depends on your implementation. Some implementations actually don't have a find max. Like if you get the max, you actually always delete it. But I prefer to put in a find max because, I mean, every time as a developer you think, oh, you know, we won't need this feature, right? And you think, oh, you know, they're always going to be deleting the max. Why would they ever do anything else? That's like, and then the first application that you go to do will be like, oh, I need the find max first. So, okay. So let's work on this. So remember how heaps work, right? So to create a heap, let's just do a recall, right? Which is a mathematician's word for learn this. The creation of a heap, basically, as a regular heap, would just be setting root equal to like null pointer, right? So that's creation. And insert. Remember what insert does. So if you have a heap, and remember a heap is structured just like a binary tree. And let me just draw out a binary tree up to a certain level. Let's do it to here. Let's say that this is 17, this is 31, this is 25. Wait, help me. No, I'm doing... wow, okay, I'm actually making it a binary search tree. Remember, it's a heap, so the maximum is going to be 82, then let's say 31, 17 like this, and then maybe 8 and 12. Here we can have 25 and 12 again. So it's possible to have duplicate values, right? And then let's say 9 and 12 again, because, you know, whatever. Okay, so let's insert, right? Let's insert 42, okay? So remember what you have to do, and this is actually homework problem 1. you have to figure out how to go here, here, and then finally here. Ugh, I cannot draw today. So, circle, there you go. So you put 42 in here, but then remember what you have to do. So the algorithm basically goes like this. You stick it on, right, as the last leaf, L-E-A-F, in the level, right? So the last leaf in the level. So what I mean by that is that if you only have 2 leaves in this level, then this is the 3rd leaf, then the next place you'd insert gives us the 4th leaf, the 5th leaf, all the way until it's literally the last leaf in the level, and then you have to go to the next level. Or first in the next level, right? And so basically you stick it on as the last leaf, and then remember what you have to do. Then what you do is you swap until heap is heapified again. And so let me explain what that means. So basically here, remember here what we can do is this compares to this. 42 is bigger, so we stick 42 in here, we stick 25 in here, and then you compare 42 to 31, and 42 is bigger than 31, so the second swap takes 31 here, 42 here, 42 here, 31 here, and at this point, then what we get to do is we get to say, well, 42 is bigger than 12, but that's not really the issue. The real issue is you compare it up to the root now, and you say, is 42 bigger than 82? No, it's smaller than 82, so you stop, right? So you stop here. So basically what happens is you insert at the bottom, and then you trickle, 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 until it's at the top. And now let's insert another few things. So let's insert, say, 17 goes here, right? And so even though that 17 is bigger than, let's make this 18. So even though 18 is bigger than these 2 nodes, it doesn't matter because it's not in the same path, right? So the idea here is that 18 is smaller than 31, so it's in a fine place. If we inserted, say, 27 here, right? If we inserted 27 here, then we would have to do some swapping. So 8 and 17 would have to come down, and 27, or whatever I picked, would have to go up here. So 27, 17, and 8. I think that's what I had. And so now what happens if we delete? So now let's do the removal. Remove is basically the opposite of insert, in the sense that what we do is we pick the last node, the last leaf, whatever that means. So basically you just look on this level, and so this is the last leaf currently, and you swap it for the root. Is it anything like bubble sort? Yeah, a little bit like bubble sort. It's a little bit like bubble sort, and in fact, there's something called heap sort. I don't know why all my P's have these big tails up top, but the point is there is something called heap sort, and what heap sort does is that you construct a heap, and then you just delete max as many times, or you construct a min heap and you delete min as many times as things in the list, and if you just keep deleting the minimum, it will come out sorted, right? Because and the nice thing about that is that the heap sort does run in n log n time. How can you tell which leaf or side to insert? So that's a good question. So actually, this is why we're about to do the array heaps, because it's hard to tell exactly where to... So the other question is, how do you tell which leaf or side to insert? My hint is from the homework problem, right? This is your actual homework problem 1, and that is what you have to do. And then my hint from that was you consider the binary expansion of n plus 1, where n plus 1 is the number of nodes. So you have to play around with that. Basically, if you label this as like 1, and you label this as 1, 0, and this is 1, 1, 1, 0, 0, 1, 0, 1, etc., then there might be a way to figure out where to go. But there's actually a reason why normally you don't implement your heap this way, because it's actually a little bit harder to do insert and delete. So basically, to delete, we swap this node for the root. So 82 pops out, and 8 goes up top. And of course, I had to make it 8 so that it would be horrible. So 8 goes up here. We delete this node, right? And then basically what we do is we have to like swapify, right? And so remember, as you're going down, you always look for the max side, because if you're going to swap for this, if you're going to swap for 27 and you swap 27 up to here, then 27 is smaller than 42, and so then you've violated the heap property. So the point is that what you have to do is you have to swap on the way down, and as you swap on the way down, so let me make this the red 42, and then 8 was in purple, so I'll keep that. And then you look here and you say 12 and 31, you would say, delete this. Well, I'd not delete it, I mean just, 8, and then this is 31. And then finally you look at the max of these two, though at this point it really doesn't matter. So then you swap 8 and 25, I think it was. And so that's how this insertion process works. Or I should say, that's how the deletion process works. Because remember, 82 was the max, and then that gets returned, right? So, all right, and then generally what you want to do is you want to throw maybe an exception if someone deletes out of an empty heap or something like that. So, okay. Okay, so you swap for the root, and then you percolate down. But always in the direction of the max. Really, I should just be typing. My handwriting sucks because I've been carrying things, and so I'm just not doing... Okay. I think the better option is just to type. There we go. Look at how much better that is. Okay. So now that we've reviewed heaps as structures, let's talk about a heap implementation. Whoops. Let's talk about heaps as arrays. Sure. So heaps as arrays basically has two operations, or 2.5 operations. You have create, you have insert, and you have find and delete max as usual. Question 2 on the homework. That's my point. Yes. So on the homework, I want you to do a left or right rotation. So write out a tree structure, which is a heap, and then I want you to do a rotation on that, and then I want you to explain why that's bad. Okay? Like, it will become pretty clear why it's bad. And so I just want you to tell me why it's bad. Okay? That's all I want. Yep, it shouldn't be too hard, given how much rotation you're already doing. So, if it is, then, oops. That could be one of the problems. Yeah, that could be an issue. So, okay, let's talk about how to do this stuff. So how do we do create? Well, so basically, when we create, you just make an array of some base size. Or, if you're really lazy, you can just use the vector class. Okay? So, maybe in my implementation, I'll even just use a vector. I was actually thinking that maybe I could implement this thing. So, let's see here. Let's make a new C-line project. And we'll call it Heaps. Right? Because that's what we're doing. And here we go. Okay. So create is pretty easy. And we also should set the number of elements equal to 0. Right? So the thing is, if you make an array of some size, then the only thing to remember is that the array size may actually be different than the number of elements in your heap. And so basically what we want to do here is this. So let me draw out an array. And let me see if I can draw out some, let's see, line segments or something. Four, 5, I guess. I wish that there was a way to like copy paste all this stuff. You know, I guess I could do it in Inkscape. That would be faster, probably, right? Where are you, Inkscape? Here you are. So let's draw out a box, and then let's draw some lines. I think, how do we draw lines? I think this is how we draw lines. Okay, oops. I'm going to copy paste. And the nice thing about this is that I can just do this kind of exponentially. So that's 4, that's whatever, 8, and then that'll be 12, and that should be good enough for our example, and then we can even make it all uniform. We can, I think it's, what is it, Control-Alt-A? Oh, it's already in the line mode. I think what I want to do is make them, oops. Do that, and then I can shift them down. Okay, so let us draw in the indices. The indices are basically 0, and then here's the index 1. Here's the index 2, 3, 4, 5, 6 is totally off. 6, let's try again. 7, 8, 9. Hope this isn't bothering anyone with OCD or AD or whatever. And then I will select it, and then I will equidistant it, and then I will do that. Perfect. Okay. So all right, so here are the indices. And then let's actually put in, so this is how it works. Basically, what happens is, when you insert, you place the object in the position of the last node. So for instance, or the first open array position, okay? So that's what you do here. So let me show you how that works. So for instance, if we're going to insert, say, I don't know, 31, we'll insert 31 into here. And so the trick is actually you don't use the 0 slot in the array for a number of reasons. I'll show you what reasons you might not want to use the 0 slot. If you do use the 0 slot, there's a slightly different calculation you have to do. Okay, so now let's insert another one. Let's insert, say, 54, right? And so when you insert 54, the idea is that at any position P, and then here's the trick to everything. At any position P, your left child is at 2 times P, and your right child is at 2 times P plus 1. So basically the way to think about it is that like, I forget if I can put an arrow on the end. I'm sure it can. But anyway, so, like, there we go. No. There we go. So, for instance, 1 is the parent of 2 and 3. And then 2 is the parent of 4, which I'll do like that, enter. And 2 is also the parent of 8, which I'll do a little bit like that. And so then 3 is the parent of 6. Well, actually, let's draw it more like this. And then 3 is also the parent of 7, like this. And you can go down the chain like this. So basically, when you do the insertion and deletion, everything is identical as a heap structure, except this is the rule. So basically here, what we're going to do is we're just going to, because 2 is a child of 1, we swap. So we're going to swap, let's see. We're going to swap 31 and we're going to swap 54 like this. And now let's insert another thing. So let's insert another thing. Let's insert, say, 27, right? 27 doesn't care because it's in the right position. Basically, 27 is in an okay position, and the reason why it's in an okay position is because it's the right child of 1, so that's fine. So now let's insert something that needs to be swapped. So you see that 2 has the children... Oh, wait, I'm sorry, not 4 and 8. That's crazy. 2 has the children 4 and 5. There you go. Yeah, and so 3 has the children of 6 and 7, like that. Okay, so now let's insert something that needs to be swapped again. So let's insert something like 82. And so 82 needs to be swapped because it's bigger than its parent. So who is its parent? Its parent is 2. So we don't ever touch 3, right? Because the children are 4 and 5. So what we do is we take this one and we swap it for 31. And so now that's okay. And now 2 is the child of 1. So we're going to swap it like this. And we're happy. Okay? And so then if we insert, say, I don't know, 43, right? If we insert 43, then 5 is the child of 2, right? So you might think to yourself, like, hey, wait, don't I have to swap this for 27? The answer is no, because the way that this thing works, 5 is not the child of 3. 5 is the child of 2. And so 54 is bigger than 43, so we don't have to do any swaps. So now, if we do that again, and we put another 43 in here, you'll be like, oh, but now 6 is the child of 3, so we have to do a swap. So 27 comes out here. So does this kind of make sense about how this is working? Basically, if you're any position P, your left child is at 2P and your right child is at 2P plus 1. This is partially the reason that they don't use the 0 coordinate. So this is assuming that P starts at 1 as the root. If P starts at 0 as the root, so if you start at 0, then the equations are as follows. So it's 2P plus 1, let's see, minus 1, I think, which is the, or I guess actually it's like, is that right? It's like 2P plus 1, minus 1, and 2P plus 1. Can you do this with vectors? Yeah, so I think my implementation will definitely use vectors. The only reason why vectors simplify your life is because if you ever reach the end of your array, then what you have to do is you have to do what a vector does, which is whenever you reach the end of a vector, it'll just allocate twice as much memory, and then it recopies everything into the new memory, deallocates the old memory, right? It does that all for you. Now, you might say to yourself, hey, wait, like, that's exactly what I want, so that I never have to actually worry about reaching the end of this array structure. Because if you allocate this as just like 1,000 integers long, then the problem is that you're just, once you reach the end of that 1,000 integers, you're either going to have a finite sized array, or a heap, or you're going to have to do some resizing operations, which means you're going to basically duplicate the thing that the vector does in the first place. So I might just be lazy and implement it as a vector. Okay, sorry about that. That was a permissions thing. Okay, so now let's talk about removal. So what happens if you delete max? So let's make a copy of this thing. So now let's run the delete max operation. Okay? So what happens is that 82 comes out, right? That gets returned. And then we just shift everything up by 1. No, right? So what we have to do now is you have to do the same deletion that you're going to do with regular heaps. So basically what you're going to do is you're going to say, who is, well, first what we do is we take the last element, not the max or the min. So first you take the last element in the array, put it in the root. So let's do that. We move this up to the root. Cool. And now what we do is now you have to percolate down, right? So sometimes we'll call this like percolation, which means you swap with the max element until you're down at the leaf level. Okay, so let's think about how to do that. Let's say that so first you pick the maximum child, so 54 is the max, so that comes up and you swap. And then you pick the maximum of these two children, which is 43, and you swap. So 27 ended up all the way back down at the bottom, but it had to go all the way to the top to get there. Okay? And so that's how you do delete max. So let's do delete max again. So if we do delete max again, oops, what you're gonna, come on, there we go. Delete max again. So what we're gonna do here is we pull out 54, you put in 27, and then you compare it with its two children. Its children are both 43, so at this point, you're basically allowed to take whichever one, because it's equal, so who cares? So let's just take this one, which is 43. Actually, no, let's take this other 43. And I'll show you why. Because we've already done the swapping down. So if we put this here in this in this slot 3, then why did I pick this example instead? So I picked this example instead because notice that its children are down here at 6 and 7, right? So this thing doesn't compare against 31, right? It only compares against this and this, but that's past the length of the heap array thingy. Okay, so any questions so far? You know, I realized, I wonder if I can, you know, if I can write on this with my tablet, then maybe I don't even need. Let's see how nice this is. Nope, that's pretty awful. Ugh. Terrible. Why not just use a regular array or a vector at this point? Because heaps have a special structure, right? That the maximum is always at the beginning, right? So the whole point here is that that find max, not delete max, but find max is an O of 1 operation. That's the point of heaps. Okay, so I'd say let's do some coding. Okay, let me show you how this works in real life. And by real life, I mean fake life. So let's make sure this compiles, because if the basic thing doesn't compile, then nothing is going to go. Hello world. Okay, so yeah, cool. So now we have some reason to do this. Let's do a C++ class. Let's call it array heap. All right. So as promised, I'm going to include vector include iostream using namespace std. Okay. So, oh, you know what I should do? I should make the size bigger, shouldn't I? Editor, font. Let's make it Python size. This is what I do in 201. Okay, so let's crush this down a little bit. Actually, I could just minimize. All right, and then, so I think we're good. Do I have Valgrind right here? No, I usually just, can I admit that I'm lazy? I just upload to the GL server when I Valgrind. I mean, though I do suggest you do that, right? I think if you can, is it a plugin or, I don't know. Anyway, I don't want to get into that right now. So let's make our constructor. And let's make our little public keyword. Let's make our private keyword. And I don't know, the things that we need are a vector of ints. This is going to be our mheap. Okay, and then we need, so keep in mind that mHeapArray.size, right? Well, actually, since we're using a vector, I guess that would be okay, as long as we're very careful, right? So, okay, and then maybe you want a copy constructor because that's the kind of thing people tend to want. And maybe you want insert, and maybe you want find max, and maybe you want delete max, and maybe, I don't know, what else could you want? Let's make a print heap function. Okay. So is everyone happy with this set of functions, right? I mean, I think I'm pretty happy with it. It's fine, right? No problem. So now what we're going to do is this. Let us copy, paste. First, let's do that, and then let's do this, and then let's do, whoops. Come on. Don't mess with me. Just be nice. Okay. So that is that. And so here the answer is do nothing. The answer here is, I guess we just copy the other heaps vector. So we just do mHeapArray, other heap.mHeapArray. Cool. For insert, I guess all we have to. Oh, you know, I am not smart. Okay, so remember what we do here. So in this case, what we're going to do, thankfully this will help us. There we go. So okay, so the point here is that this is putting the value on the end of the array. So now we have to do the percolate up feature, which is basically, let's say our position is equal to mHeap Array dot size -1, and I guess I have to make it an integer, or I don't know, probably unsigned, right? They hate it, and by they I mean C++ hates it when. Okay, cool. So what you gotta do in this case is, you know what, actually we could just do, we can make this a for loop. Dupe, pause bigger than 0, pause divided equals 2. There we go. Is everyone happy with that? This is basically like, equivalently, it's like while pause is bigger than 0. And so remember, let's keep the array indices correct. So let's make sure that in this case, do slightly more than nothing. So what we're gonna do is just put in a crap value. So mHeap Array dot pushback crap value. Define really, I mean, it doesn't matter. Let's just make it 0. Okay. Why is it not like that? Expected expression. Isn't that happy? What's the oh, because it's that, yes. Yeah. Okay, so heap.pushback crap value. So now what are we going to do? Basically what we're going to do is we're going to check if the thing at position pause is bigger than the thing at position pause divided by 2. So if it is, so let's do this. Actually, I think we want it to be bigger than 1 in this case. I'll show you why. If you make it bigger than 0, then it's going to try to swap with a crap value. But if you make it bigger than 1, then the last thing it'll do is swap with the root, which is what you want. So if mHeap Array at pause is bigger than mHeap Array at pause divided by 2, then we want to swap. So int temp equals doot equals doot, and then sure, doot. Cool, right? So this is what we want to do, and all this is doing, right? This is just swap. This is a canonical swap, and then I think this is done, right? Or am I dumb? I don't know. Who knows? Let's test. So, in order to test, I think I would like to print out the heap. So let's just do for auto x mHeap Array I'm using all those advanced new 2012, 2020 C++ features. Look at that. C out X, and then we'll C out a space. Why don't we, even better, we'll C out open paren, never mind. Let's just do the standard way. And it always yells at you if you don't make this unsigned, because it's comparing it against size, which is unsigned. Can't use the advanced feature. So let's do this, and then a comma. So this will be the index, and then we'll output heap array at I, and then we'll output the end paren and maybe some spaces. Okay. How about that? Does this look okay? I don't know. Let's test. So let's say return 0 here so it doesn't yell at us. Let's return 0 here so it doesn't yell at us. Okay. Let's run it. Let's make a simple test function. So our array heap. So let's say while I is not equal to 0, and of course I do so much Python programming that I forget everything about int I, cni. So the only value you're not allowed to insert is, let's just say only positive values go into this heap, so no negative values. And then what we're gonna do is we're gonna do array heap and then we're gonna do insert I, and then we'll cin I, and then we'll dot print heap. Okay. What do you think? Is this a decent enough test function? I think so. So let's run it and see what happens. How many errors? Did this just run? I don't believe it. That's crazy. So let's insert 5. Cool. Let's insert 17. Ugh, help me, please. Look at that. Okay, you see here, so the crap value, so 0 has a crap value in it, so never pay attention to the 0. In fact, what we should probably do in our print statement here is we should probably just say I starts at 1, and that would fix that. And so now let's input 13, which is a child of 1, so hopefully there's no swaps. And let's do 19, which is going to swap with the root. So 1 is going to come down and be at element 4. 17 is going to, 17 is going to become element 4, and 19 is going to go up to the root. I totally lied. What happened? Oh, no, okay, I didn't lie. It didn't come all the way down, it just, okay. What happened? So let's see. We put it in element 4. Yes, and 4 divided by 2 is 2. Oh, it had to swap with 2, right? So, okay. It had to swap with 2 first. So that's why 5 came down. See, my algorithm is right. I just couldn't read. Okay, let's do 31. So 31 is going to swap up to the root. It's going to swap through, so 17 is going to come down. 19 is going to swap down. 17 is going to swap down. 31 is going to go all the way to the top. There we go. Now let's do, so now we're talking about children of 3, right? Because the children of 3 are 6 and 7. So let's do 8. That should stay where it is. Let's do 9. That should stay where it is. Right? And the reason why is because 13 is bigger than 8 or 9, so that should stay where it is. And what else should we insert? Let's say 25. So what happens when we insert 25? So when we insert 25, 25 is the child of, or I should say, spot 8 is the child of spot 4. So it should swap up to here. And then spot 4 is the child of spot 2. So 19 will come down here, 5 will come all the way down, and I think at 2 we'll end up at 25, right? So yeah, 2 ended up with 25, 4 ended up with what was at spot 2, and 8 ended up with what it was at spot 4, which was this 5 value. Any questions? Any questions about this so far? Right? We've done insert. We haven't done delete, so, you know, whatever. But now let's do delete. Let's make a class. Yeah, I guess that's all we need. It doesn't even have to have much. We can just throw it. Okay. Okay, so we need to do this. Yeah, there's nothing wrong with negative numbers. I just had to pick some condition to exit. And so 0 or negative is just going to exit. So find max. So basically, how do we find the max in the heap? So we check and we say if array heap, or heap array dot size is bigger than or equal to 2, right? Then we can return, what do we return? We return heap array at max pause. Yeah. So let's define, you know what? There we go. You know, if you were really C++ in it, should probably define max pause to be 1, right? But you know what? We're being lazy. Okay, and so if it doesn't return here, then we want to throw an empty heap exception. Okay? Why does it not like this? Okay, let's do it. Do you have to include exception? Okay. Maybe it's something like that. Why does it not? What is it mad about now? Incomplete type. Oh, because this is Python. Well, you would need a catch. Yes, you do. So I'm an idiot. This isn't Python. So, okay. I don't need to leave that because no one will understand now that it's correct. Okay, so why don't we just, oh, and maybe in order to avoid the exception, we'll have a bool empty. And so this is basically just to avoid if you don't want the exception to be thrown, right? And so basically we'll say return heap array dot size is bigger than 1, right? And so the thing is that if it's bigger than 1, then that'll be fine. Okay. So, okay, so let's do delete now that we've done all this stuff. So this is, where did I do find? Find max is here. And, okay, actually we can copy paste the same code for delete max. The only difference is that we have to do some stuff in here now. So let me see. How do you do that? That's a good question. Let's see. God, I forget now. I forget so much. So let's see. Heap Array dot delete dot remove dot how do you get rid of the last thing? So I'm sure that you can you pop? Ooh, does pop back work? That seems right. So int value equals this. Actually, wait, why doesn't it like this? Cannot initialize a variable of type int. Oh, popback just, does popback just delete it? Okay. So I guess what we need to do is we need to get the value before we pop back. So, okay. Let's just do return value is equal to mHeapArray1, and then we'll do mHeapArray1 is equal to mHeapArray there we go. Okay. So, and then instead, so you see why I had to define the return value? Because what I'm doing here is I'm copying the thing at the last position up into the root value. So copy the thing at the last position into the root value, and then kill off the last position. And so now what we need to do is percolate down, right? We need to fix the heapification structure. And how do we fix the heap structure? What we do is we say, I don't know what we say. We just say, if it's bigger, right? So if, so we go, while the position, let's say position is equal to 1, and then we say while position is less than mHeapArray.size, and so we might have to fix that up in just a second, but that's a good first approximation. And so then here's the issue. There's a lot of edge cases. So welcome to the land of edge cases. And so what are the possible edge cases? Well, the edge cases are basically like this. Well, maybe it has 2 children, in which case, not an edge case, right? So if 2 times position plus 1 is less than or equal, is less than mHeapArray dot size, then, and you notice that I will continuously do Python stuff. Then you swap with the max on the way down, and then we set position to be the either 2p or 2p plus 1, depending on which one is the max. Okay. But what are the other edge cases? So this is the has both children case. What about else if 2 times position is less than m heap array? And so what if so what this case is basically that it doesn't have a right child, only left, right? So this means that we're almost at the bottom of the heap. We're at one level above the bottom of the heap. It has 2 children. One of them is technically null pointer, except now we're using arrays, so it's just not there. And the other one is, well, what is the other one? The other one is just a child, so we have to look at that child only. So look only left if bigger, or if the child is bigger, swap down. And then here, well, we don't really need this else. The else is like there's no children, right? So, so then there's, there's really like an else no children, so no swapping. So, okay. Let's try to figure out which one's the max. So basically, and what do I mean by which one is the max? Remember, it's not which one is bigger than the node. It's if Heap Array 2 times position is bigger than Heap Array 2 times position plus 1, then left is max. Else I hate how it does that. I really want it to just be like, I want it to do that. I mean, we're in C++. This ain't JavaScript. What is the problem here? Doesn't seem to like this. If statement has identical branches. Oh, it's because these are identical. So then you say if Heap Array at the position is less than Heap Array at 2 times position, then what you do is you swap. So int temp is equal to, and then let's just do our standard swap. Right, this is swapping down. And then 2 times position equals temp. Okay. And then else right is max. Oh wait, no, I'm sorry. This is if the left is the maximum. This is if it needs to be swapped. There's actually no else. Okay, there we go. So there we are. And then here what we're going to do, and if the right is the maximum, then we want to compare. So if the right is the maximum, then we say if Heap Array at position is less than Heap Array, but this time it's 2 times position plus 1, then we swap. And the only difference here is that we need to add the plus 1s to the 2 times positions. So it kind of sucks in that sense, but whatever. And then what we can do is we just say position is equal to 2 times position plus 1, because that'll tell us our new position. And here our position is 2 times position without the plus 1. So this is all the general case. Basically, this is basically if the left one is bigger, then you check if it needs to be swapped and you swap. If the right is bigger, you check if it needs to be swapped and you swap. Okay. So now what if there's only left? So if there's only left, then really we can just copy paste this code, right? Yes. Oh, and if it doesn't need to be swapped, I guess what we can do, in order to exit the loop, we can do this. We basically will just say position is equal to Heap Array dot size plus 1. Right? So basically that is, what are we doing here? We're saying this doesn't need to be swapped. What's the problem there? Oh, it doesn't like the unsigned to signed. Fine. I guess it's not going to like the comparison either. Let's just change that. Okay. Else no children, so no swapping. So actually we will have an else. The else condition will be this. Dot size plus 1. Position equals. And so you see why I'm doing that? I'm only doing this because the thing is that we have this while loop, and it won't terminate unless the position is not less than this. So I'm just setting it to 1 bigger. Technically, I could set it just to mHeapArray.size, but I like feeling safe. I'm just going to set it to size plus 1, and I'm pretty sure at that point it should be outside. And so here, we also know that there doesn't need to be any swapping, so we can just set it there. So this is a lot of code, right? But you see that the code isn't actually that complicated. It just has to consider all the different cases, right? This is if you have 2 children, this is if you only have the left child, and this is if you have no children. So no children means no swapping and you're done. You know, this means that you have to look at the left child only, and this one means that you have to look at the maximum of the 2 children. So if the left is the maximum, then you do this. Else, if the right is the maximum, then you do this, and then you are done. So, and I mean, what is that? So that's about 140 lines of code. So I would say not too bad, right? Not too bad. So let's test this out. Let's do. Will I post this? Will I post this code? Yes, I will post that code. Okay. So we'll always print. We will. So I think what we want to do is this, and then we can do. We'll have to copy paste this garbage here, and then what we're going to do is this, else if thing equals delete, cout, okay, I think that's good enough test code. And then we'll always print the heap, and then Python again. Okay, there we go. So let's do this now. How many bugs do we have? Did it work? So let's insert 5, insert 10. Wait. Oh, wow, we can do that. Because it CNs both things. Insert 15, insert 25, insert 71, insert 225, insert 2. All right, now let us find max. Not a surprise, it returns the right thing. Now let's delete max, and this is, you know, are you scared? I'm a little scared. I'm gonna hit it. Okay, did it work? So this is our old one. So what's gonna happen when we hit delete? So it gives us the right max, which is not surprising. But what else should it be doing? So it needs to swap the maximum of 2 and 3 up. So it swapped 71 up, so that worked. And so now it had to set the position to 3. So now it's looking at 6 and 7. So it should swap 6 up. Oh, I'm sorry. Yeah, no, it should swap 71 down. Ah, crap. So it's going to put 2 up here. It's going to swap that down here. And then it's going to swap that down here. Yes, so we're going to end up with 10 here. Did we end up with 10 in position 3? Yes. 71 in position 1, 10 in position 3, and 2 all the way down. See, 2 got removed from position 7. It was the other child of 3, and now it's the left child. So it was the right child that got deleted, and now it's back up at the left child. So now let's delete again. Cool. That looks like it worked right. Delete. 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 And finally, ready, set, debug error, right? Abort. So that happened because we did not catch the exception. So we should try, and then we should say catch, what was the exception called? Empty heap exception, E. And then we want to see out, there was an empty heap, you naughty human. Why doesn't it like this? Oh, it should catch by reference. Okay. You know what? I'm okay with that. I don't really care. If you want me to catch by reference, I'll catch by reference. You know, I'm happy to oblige. So let's rerun the code. And then what we want to do is like insert 100, insert 200, insert 300. I guess I'm going to insert 200 again. 81, insert 438. Or no, it's 538. And then we want to insert 71. And so we're pretty sure that insert works. Notice here that this is not exactly sorted, right? The reason why it's not exactly sorted is because the left and the right children don't care, right? So all that 2 cares about is that 4 and 5 are smaller. All that 3 cares about is that 6 and 7 are smaller. It doesn't care that 3 has children that are theoretically, well, actually they're not bigger. But if they were, if this one was like 250, this position here would not care because these are not its children. Okay, so now let's do deletion again. Delete, 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 delete. Insert 5 again, just to test. Delete, delete. And finally, delete. Okay. So I think that this is a pretty simple data structure, but it's also definitely kind of an interesting way. And basically the trick here is that whenever you have what's called a full binary tree, and a full binary tree is anything where you have basically every level is filled except for the bottom level, and the bottom level is filled up to a certain point from left to right. That's what a full binary tree is. And so if you notice, the heap structure is always a full binary tree. So you can represent it as an array. If you wanted to represent a regular binary search tree as an array, you could also do that. The only problem is that you'd have to represent emptiness somehow. There'd have to be an empty value. So, yeah. Well, come on up here. Huh? Okay. You want to come on? No? Okay. All right. That's That's fine. Pupper, come here. Come here, Pupper. You're slightly under the gate. Come here. Come on. So I think Pupper says that the lecture is done, right? I think that's her opinion. I could be wrong. It's hard to know what dogs think. So, yeah, she's not that bad. So, okay. Yeah, she's probably smarter than I am. So, okay. I think after that, I will let all of you go. Am I available after class? Yeah, I can sit around. All right. Yeah, so anytime, I think the answer to that is yes. Anytime you search for a node, you must splay that node. The dog is always available. If you really need the dog, she is available. She doesn't have a job or pay rent. So, bad dog. All right, I'll let you all go. Now, this class didn't turn out to be so bad. Yeah, so insert, you definitely have to splay. And every time you find a node, you either splay that node, or if the node isn't in the tree, you splay the last node that you searched. Okay, outro.